Hello,
Hey, how are you?
I'm good. How are you?
I'm good, thank you. Okay, what's new?
So I took my practice test yesterday and I feel like I'm doing better, which is good. I just still need to figure out like what is going on with Chem Phys, but I feel like Biochem is going fine and Psych Social is going okay. I don't know.
Was this the full length three?
No, I took the unscored one.
Oh, I see, I see. Oh, okay, nice.
Yeah.
Your score went up 6 points from last time.
Yeah, I'm
Mhm.
happy about that for sure. Um,
Very good. Okay, cool. Yep. What were you gonna say?
but I said, yeah, I'm happy about that for sure, but I feel like ChemPhys isn't like moving, even though I was hoping that it would.
Got it. Yeah. Okay.
And I worry, I mean, I don't know, I feel like maybe the reason why I wasn't doing so well in psychosocial 4 is because I'm always like tired when I get there. And I feel like this time I was really like forcing myself to like read and like stay awake.
Mm-hmm.
Um, I don't know if that had to do with my score because I was kind of surprised. I was like, I feel like I still need to like sit down and like memorize everything for psych soc. So I hope it's not a fluke. But I don't know. I feel like that's a section that I could do well in. So I would like to get pretty good at that. In biochem, I feel like it's all coming together now for biochem at least.
Got it. Yeah, psych social a lot of times is just, you know, content stuff that like even if you completed like your content review, it's like each test will show you new material that like review books don't, and so you just have to learn that new material from each full length that you take.
Hmm.
Oh. Yeah, it's okay. That's promising. And yeah, let's look at what's happening with CP.
Okay, let me share my screen. Mm. Although I'm supposed to be working today, but maybe that's not it. Well, this one. I'll just share my whole screen. I guess I'm like working from the library, so I'm not like not on campus. I'm just not at the hospital right now. Like I don't know how to switch like move this top thing. Hold on.
Or score report? What are you trying to access?
Um. Oh yeah. Can you see it? Wait.
Hmm. Yeah. Tab for score report. Is that what you're talking about?
Yeah. I'm
The
trying to access the tab, but it's like what do you call it? The Zoom thing is blocking it. I was trying to move it.
okay.
Okay, there we go.
Hmm.
Okay, better. So this is what I was working on. I mean, I feel like the questions I got wrong in Canvas are like just like a lot of what's it called like OChem
Hmm.
stuff. Like I was confused about this.
Yep.
Um, it
Yeah.
says that there's 5 chiral centers, but I'm like, I just don't see it. I thought this would be one, like the oxygen itself. I thought this would be chiral.
So
I didn't.
for a carbon to be chiral, it must be bound to four different things.
Right. Oh, it's double bonded. Okay, never mind. I was like,
Hmm.
okay, yeah, okay.
Hmm.
Um, so isn't this carbon here, this one right here, it says it's chiral, but it's bounded to another carbon and then another carbon here, or is this one actually bound to the nitrogen and they just drew it like that?
So no, so that's a good question. So when we consider the things that it's bound to, we also consider what, so like if something's bound to another carbon, what that carbon is bound to also plays a role in whether it's, the same thing or not. Um,
Hmm.
so for instance, this carbon here is bound to the OH. It's bound to a hydrogen, which we don't see. And then, yes,
Hmm.
carbon and this carbon, like they do appear to be the same, but this carbon is bound to the nitrogen, and then this carbon, whoops, this carbon is bound to another carbon. So we consider that. But
Okay.
yeah, but something that can assist in that is that for anytime you see a wedge, that
Hmm.
like indicates if something's going like into the page or out of the page, and that's only used on chiral uh carbons. Um, and that could be kind of like a shortcut to finding your chiral centers. Because if you think about it, if it wasn't chiral, then there would be no need to put the wedges in.
Okay, that makes sense.
Yep. And then following from that, since there's only so when you have so basically, okay, if a carbon is attached to a wedge, and actually like I know this one is kind of attached to a wedge. I mean, it's like not coming from that carbon, but it could be kind of confusing because it's attached to the wedge. But, now you can see that the carbon's attached has a double bond to the oxygen, so that can't be chiral. But in general, um, yeah, looking at your um carbons that have a wedge coming from it rather than to it. So like in this example here, the wedge is coming from this carbon, and then what it ends up connecting to is not going to be as important. So we can see that, okay, wedge, a carbon with a wedge here, 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 carbon with a wedge there.
I see. So that's like five.
Let's see, one, two, three, four, five. And then to figure out the number of stereoisomers, you could also see that if there's a wedge, there's only two possibilities, right? A wedge that's dashed or a wedge that's whatever black.
Hmm.
That must mean that, so okay, if I just drew, let me just draw like a very uh molecule like this. Let's say like an OH here or something. Um, and let's say this one here, it's like a black wedge. I'll say like another OH or something like that. So here we have two chiral carbons, one here, one here. And then if we think about the number of stereoisomers they can produce, this one at this chiral center here can have a stereoisomer where this wedge is like, let's say dashed, or it can be when it's black. So that means that at every chiral center, you can have two possibilities. Okay?
Okay.
So then that would mean that there's, two possibilities here, two possibilities here, and ultimately that will give you four possibilities, like one where, let's say this is like black and then this is dashed, one where there's both black, one where they're both dashed, and then one where this one is dashed and this one is black. So ultimately that comes to this equation, 2 to the power of n. Now that 2 comes from what I said previously about how each, like for instance, like, okay, this entire molecule, the way it is one stereoisomer. And then I
Hmm.
can make this one black. That'll be the second stereoisomer. And then I
Yeah.
can make you know, have it return to just being the wedge, and then make this one the wedge with the dashes instead of the black wedge. So that'll add
Mhm.
another one. So basically, this equation, 2 to the n, where n is the number of chiral centers, will be the equation for the total number of stereoisomers.
Okay. Okay, that makes sense. I was confused because it was like it says here 2n, so
Oh
but
yeah,
it's 2 2.
that's them, you know, messing up and because like I guess they wanted to write 2 to the n power, but it comes it comes out as just 2n. Like they could have
Okay.
written 2 up, arrow n, but I don't know.
Oh, okay, that makes sense. Let me just yeah, so I guess it's yeah, okay, 2 to the fifth is
Hmm.
32.
Hmm.
Okay. I feel like I messed this one up. I was kind of confused. I mean, I know now that it's A, but I don't know. Before I put C for some reason. Okay, let's get that.
So wait,
Um,
made sense or not?
yeah, it makes sense. I mean, I was just thinking about it from like a how the myelin sheath like speeds up the action potential point of view. Um, so I was thinking, I don't know, I was thinking more so about like conductivity, and then I just knew that Schwann cells are like a form of myelin sheath, but it doesn't necessarily produce Schwann cells. Like I feel like like Schwann cells aren't they like they're like a type of myelin?
So they're the ones that produce or make the myelin, right?
Yeah.
So, um, like the function of the myelin sheath to produce Schwann cells would be kind of like the other way around. The Schwann cells are the types of cells that make the myelin sheath.
Okay.
Like if this is a neuron, like let's say something like this, um a Schwann cell, let's say S here, can like kind of wrap around the neuron, like the axon of the neuron, and produce that myelin sheath. And in the brain, it's done by Schwann cells. In the rest of the body, it's done by oligodendrocytes. Let me get a picture for you here. Um, Here, I put a picture in the chat. Yep. So we have. Mhm.
Okay, never mind. I was gonna try and move it, but it's not going. It's fine.
So
Okay.
yeah, so it's kind of hard to see here, but here in this view, you can see that the Schwann cell is kind of like, or maybe over here, it's a start. Okay, so you can see that we have the axon here, and then this blue thing around it is the Schwann cell,
Hmm.
and then it can kind of like wrap around the axon producing the myelin sheath, which wraps around it like this.
Yes. Cute.
See, yeah. So you can see that, yeah, that the Schwann cell makes the uh the myelin, the myelin sheath.
Yeah, it's like a little blanket. Okay, cool, cool. Um, okay. So I guess like
And
so I,
sorry, one last thing. So it was the other way around. So the Schwann cells work in the peripheral nervous system, and the oligodendrocytes do the same thing in the central nervous system. So that's the difference between the two.
gotcha.
Mhm.
Oh yeah, I was gonna ask, okay, so I guess like the main goals of the myelin sheath are to provide insulation and to, because I know they speed up the action potentials too.
Oh, yes, that's their main function. So for instance, if I had some, neuron here, um, an action potential can just go down that length of that axon. Um, but what the let's say that we have either oligodendrocytes or Schwann cells making myelin, which is this, it's like a fat, it's like a type of fat. It makes it so that the action potential, instead of, it's a little weird because it like kind of prevents the action potential from going right through it, but it causes in order for the action potential to still proceed, it has to jump from these, so in between the myelin sheath, like, here, let's say, and here. It's kind of not drawn here because this is supposed to be the Schwann cell, but uh, in between are the nodes, they're called.
Hmm.
And so
Yeah.
the action potential jumps from node to node. This is called saltatory conduction, and that means it's like Latin for jumping because it jumps from node to node to node to node rather than going
Okay.
right through. So it increases the uh, velocity, the speed of that action potential. So like in our brains, white matter is, distinct from gray matter in that white matter is myelinated axons, and gray matter is just, unmyelinated. So white matter, has faster conduction because of the myelination.
Okay. Some? No, sorry. All right.
Yeah, so that question, if you go back to that, um, yeah, so that would be that, right?
Mhm.
Okay.
Um, this one I was just confused because I just assumed that the chlorides were the smallest, but I guess it's sodium, but I wasn't quite sure. I thought they were basically all the same size. This one definitely tripped me up, but
Oh, remember when we talked about ionic radius and how that's different from atomic radius?
oh yeah, yeah, yes, yes, we did
Mhm.
in the
So,
trends.
mhm. So,
On this one.
so from that, do you remember that, like which types of like ions were like bigger, what types were smaller?
Mm, so I feel like these these ions are, because I think those are like the earth metals. I think these are the they're bigger
So it
than sodium.
it's less of a thing with like the atomic radius trend and more of a thing with just ions. So for instance, um so if we say that like an atom's radius is based on the distance between the protons in its nucleus and the electrons surrounding it, right? Because the protons in the nucleus are kind of pulling, since they're attracted to the electrons, they're kind of pulling those electrons in close to itself, like as much as it can, right?
Hmm.
And so this can give us the like atomic radius. Now, if you imagine like this same type of thing, but let's say we added another electron, will it be able to pull it in as close?
No.
Correct. And then if we removed electrons, like it would be able to pull it in closer, right?
Yes.
So so the so the thing about the ionic radius is that compared to a neutral atom, the cation, which is, the positively charged ion, will always be smaller than the regular atomic radius. And an anion, which is when it's negatively charged, which means it gains electrons. The protons, you're not gaining protons or anything, so it's the same amount of protons that have to pull in the uh, additional electrons now. And if it's has to spread that kind of like pulling force across more than one electron, it's not going to be able to pull it in as closely, right?
Yes.
So that means that your sodium and potassium ions are going to be smaller than the chloride ions, right?
Yeah.
Hmm.
Okay. Gotcha. So then,
Yep.
okay, so then I guess like in terms of ionic radius, sodium is smaller than potassium because it's like above it.
Oh, so yeah. So now since we're comparing, so like first that let us, compare cations to anions. And
Hmm.
we know that cations are smaller, but since there's two choices for cations, then we can also use the atomic radius. So sodium, or rather, yeah, sodium. So atomic radius gets higher if you go to the left and down, right?
Yes.
And so
Hmm.
sodium is above potassium, so sodium is going to be smaller, a smaller atomic radius. Um, and both sodium and potassium are cations, so we know that, we're going to choose one of those. But yeah, it'll be sodium because it has a smaller atomic radius than potassium and smaller ionic radius than chloride and your proteins.
Gotcha. Mm. Yeah, I was confused by this. Because
Mhm.
I was like, is this like a capacitance question?
Um, let's see. So it's asking what's the closest distance okay, so the NCV test here. So scientists can study the electrical properties of neurons by inserting probes into them to measure voltage changes as a response to stimulus. Um, the typical plot of this action potential is shown in figure 2. So we have figure 2, a typical nerve impulse. also known as the action potential. And we see like this type of thing, like does it look familiar? Like this shape?
Yeah. That's
Tell me about it.
um so it shows like the sodium ions going in.
Where?
Call, probably like over here.
So, so in general, this is like, um, so like, okay, so the neurons like cell potential is like down like negative 70-ish right here, right?
Mm-hmm.
And then if an action potential is made, yeah, it'll open up the sodium channel, and what would that cause?
Depolarization.
And that's caused by what?
Sodium going inside the.
So basically, the sodium channel opens up, right? And
Mm-hmm.
because there's a larger concentration of sodium outside the neuron than in, the sodium goes inside the neuron, right?
Yeah.
And since sodium is positively charged, it makes this neuron more like less negative, more positive. And yeah, that's your depolarization that's happening. And up here around like plus 40 or whatever is the end of the depolarization. And
Mm-hmm.
so your sodium channel closes, but now your potassium channel opens up, right?
Yeah.
And tell me about the relative concentration of potassium, like inside the neuron compared to outside.
It's super high, so the potassium will go outside the cell.
So you're saying it's super high inside the cell?
Yeah.
Yep. And then, so then you'll have potassium efflux, right? It's going to leave the cell, the neuron,
Hmm.
and then you have this, it's going to become, since it's losing positive charge, it's going to become more negative again. And we call that repolarization, right?
Yeah.
And now the thing is that the sodium channel is fast. It can open fast, it can close fast, but the potassium channel is slow. So it's going to be slow to open, slow to close. So that's why it's going to overshoot and go a bit more negative than, it's supposed to. And we call that hyperpolarization. And you can kind of think about this like, okay, the way that the way that the neuron is negatively charged at the beginning, we can just say it's polarized.
Hmm.
You don't really call it that, but if you think about it that way, then you can see that as it so if you could say that it being negatively charged inside the neuron is polarized, then you can see that when we make it less negative, it's depolarized, right? And then when we make it more negative after the depolarization, it's repolarized. And then if it goes beyond and gets too negative, it's too much polarized, so hyperpolarized.
Hmm.
And then it'll slowly come back to the normal levels, right? So now the NCV thing that they're talking about, a nerve conduction velocity test, so they're saying it exploits the electrical properties of neurons to test for nerve damage. In this test, two electrodes are placed on a patient's body with an electrical shock placed on one and the nerve response measured on the other. And the pulse travels at a constant speed of 100 meters per second. Okay. Um, Now let me take a look at this table here. If they say, okay. Okay, yeah. So non-myelinated compared to myelinated. Axon radius is the same, and that might seem a little weird, but I guess it's because the axon radius doesn't really change, but when you add the myelin sheath around it, it can make the overall thing thicker, but the axon is still the same thickness. It's just that the myelin around it makes it thicker. Um, and okay. So they're at, so yeah, we can go back down. So now here in this in this NCV test, it seems like, okay, the distance between these like notches on the x-axis is 1 millisecond, right? So we can see that the whole like depolarization, repolarization happens within the notches. So this happens within 1 millisecond, right?
Yes.
Okay. So okay. So they're asking what's the closest distance the electrodes used in an NCV test can be placed on a nerve in order to measure the voltage change as a response to the stimulus. So, so we are given or we're being asked about a distance, and the passage gives us a speed or a velocity, and this figure 2 gives us a time like interval of 1 millisecond, or at least, 1 millisecond for the entire yeah, I guess, action potential to happen. So we could use the time and the velocity that they give us to find a distance.
I see. I feel like I did not notice that that graph had like the millisecond thing in there. I just didn't notice it. I feel like
Yeah,
my
yeah.
bad.
This is a pretty I don't know if I should say unfair, but like if you scroll up on the passage again, like this passage is giving us a lot of information at once. So, like, how do we know what's important and what's not important, right? So they're starting off
Mm-hmm.
by telling us that the CNS is an example of an electrical system. Neurons are the basic electrical components. There's three classes: sensory, motor, and inter neurons. So some info about that. So sensory neurons are like, if you like touch something, it would activate like a sensory neuron, which will send a signal back to either your brain or your spinal cord. It like if it's a reflex, it's like just your spinal cord. And from the sensory neuron that gets the information, the interneuron connects the sensory to the motor. The motor is when you can send the signal out to like, so let's say it's like a hot stove or something. You touch
Mm-hmm.
it, it's like sends through the sensory neuron, like, oh, this is hot, sends it. And I guess since we're talking about like not going to the brain like a reflex, it doesn't have to go all the way to the brain. It could just go to the spinal cord, um, interface with a interneuron, which connects the sensory to the motor. And then from the interneuron to the motor, which controls, like our muscle movement and stuff. And then our motor signal comes back to our hand on that hot stove and goes like, takes it out, moves it. So, um, yeah. So in that situation, like it doesn't have to go to the brain because it's like a really fast reflex. So,
Hmm.
okay, then they say each neuron is made of three main components: the nerve cell, the axons, and the dendrites. Um, well, the entire thing is the cell, but I guess they mean like the nerve cell body,
Hmm.
which is called like the soma. It's like this part, and then the axon is like this long part, and then the ends of it are the dendrites. Um, And then they say the longest axons are approximately 1 meter in length, and the axon outer membrane is surrounded by an extracellular aqueous solution of protein, sodium, potassium, and chloride ions. And then they give us some summary of the products here. And so we have, a bunch of kind of information given to us. And oh yeah, cool. So over here you can see that the myelinated axon, although they both have the same axon radius, the thickness of the myelin or the membrane, if there is no myelin, is much smaller for the non-myelinated axon, right?
Hmm.
So we can see that the myelinated axon's, thicker. Um, and then this figure one here, it looks like horrible. Um, and we end up not even really using it here. So
Yeah.
so that's where it could be a little uh I guess like unfair, but anyway, let's see. So for this question, so yeah, we have okay, 100 meters per second and the time of 1 millisecond, which is 1 e negative 3 seconds. And using this information, we can find our like distance, the closest distance that they could be.
Okay. Oh, okay. This is this one.
Let's see, right? Um, so yeah, I'm rewriting the 100 meters per second in scientific notation. It would just be 1 times 10 to the 2 meters per second, right?
Yeah.
Now, our what do we do with this time? Do we like multiply it? Do we divide it? What do we do?
Mm, multiply it.
Yep.
Yeah, multiply it times the meters.
Mm-hmm.
And it's the negative one.
Mm-hmm. Yep.
So I'm like, it's not that. It's
Yep.
I could have sworn I put this, but whatever. I guess I put this.
Wait,
Oh well.
what were you saying?
No, no, no. I was just talking to myself. It's fine.
Okay.
Chill out.
So so yeah, for the math, um, even though it might seem simple, just do it in a systematic way to avoid any type of possible mistakes.
Yes. Okay, this one I was so confused. I feel like I should know how to do this. That's why I was kind of frustrated.
Mhm.
But
Yep.
I blanked, I guess. Is this like another KSP question? Because that's what I was trying to do.
Uh,
Um,
so, um, so not exact, like it is similar to a KSP question, like problem, but we don't have any, like KSP is what it really represents is the maximum concentration for at which that thing could dissolve.
yes.
But this one, we're not giving KSP or anything like that because they're telling us that it's already a solution of this. So, and they're asking for like this chloride ion, so it's already dissolved, but it does require you to know like what the chemical formula of this is, which isn't really like something you have to know. It's something that you can like kind of figure out based on
Yeah.
charges.
Isn't it? It's CaCl₂, right?
Yep.
Yeah. Um, so then like I guess like so like point 0.1 molar is like zero point 0.1 moles per liter.
So you said CaCl2, right?
Mm-hmm.
And then what is this dissociating?
Oh, to Ca2 plus plus Cl um Cl2.
Cl2 or
I guess Cl minus.
but two of them, right?
Oh, okay, yeah, 2 Cl minus. Okay, that makes sense.
Because if you think about it, if you did Cl2 like this would have no net charge, right?
Right.
And so if you have this with a charge and this without a charge, this over here should be 2 plus, right?
Oh, okay. Yes. Yes.
So this is also related to something called like the Van 't Hoff factor, um, which is represented by like a lowercase I. But the idea of this is like, so let's say we had magnesium chloride, right? Or rather,
Mm-hmm.
sorry, not that. Sodium chloride, right?
Yes.
If I had 1 molar of sodium chloride, that would break apart into Na plus and Cl minus, right?
Yes.
With one of each, right?
Mm-hmm.
So then I could say this is 1 molar and this is 1 molar, right?
Yeah.
But over here, if this is 1 molar of CaCl2, this would be 1 molar, but this would be 2 molar because it breaks up into, so like this one, NaCl breaks up into two. CaCl breaks up really into three. I mean, it breaks up into two different things, but ultimately it breaks up into one calcium and two chlorides.
Okay.
Hmm. So,
Okay.
yep.
So, oh, I guess it's not as bad as I thought it would be. Okay, so it would just be zero point 0.2 molar instead of zero point 0.1.
Hmm. Yep.
Oh, excuse me. It's like I feel like I was trying to overcomplicate it in my
Mhm.
mind. Okay, so that's how it works. It's like that for most of like I guess like the I guess this is like a ionic dissociation, like
Uh-huh.
when it's Okay, so it'll always just be 1 molar of sodium, 1 molar of chloride, and then 1 molar of calcium, and then if there's two, there'll be 2 moles.
Uh-huh.
Okay. I don't know why I was thinking about it way too much. That's not that bad.
Yeah, so like the way to think about it is, if you go back to that, is first calcium chloride. What does that look like? Right? You get
Yes.
that. And then you see, okay, what does it break up into? It breaks up into this and that. And in order for the calcium chloride to be neutral, right? What it breaks up into over here, if you add the charges, must be uh neutral, right? So like the 2 plus from the calcium has to be in addition to something that would cancel that 2 plus out, right? So if it was just like Cl2 with a zero charge, this would be charged. But since this isn't charged, these two must be charged and they must be balancing each other out.
Okay.
Mhm.
Gotcha. Yeah, I don't know what this one was even asking.
I
I think it was just asking about the shine, but I was like, what? What
so
is this?
this is this is okay. This is a bigger topic here. So remember how we talked about every biomolecule know like the functional group of like whatever that type of bond is?
Yes.
So like a peptide bond is like an amide, right?
Mm-hmm.
And then like between like a glycerol and the fatty acids to make a fat would make what type of bond?
You said glycerol in the fat.
So here we have glycerol and here we have, let's say, three fatty acids.
Oh yeah, that's a hydrogen bond.
Uh, well, so something happens here from adding these that makes it like a real covalent bond.
Oh, it's condensation.
Uh-huh.
Uh,
So, also known as dehydration synthesis. Yep.
So then it would be a ester.
Very good. Whoops. Oh yeah, like that, right?
Yeah.
And then, more. But good, 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 good. Um, now, we talked less about sugars, but let's say we have a glucose or whatever here. Um, like, an OH here.
hmm
And let's say this is an H here. Oops, an H here. What functional group can this be now? And I'll draw it like this.
So is it alcohol? Oh, a hemiacetal. Yeah, those.
Yep. And then if this was just another R group, then that would just be a hemi-ketal. Okay. Now,
Gotcha.
uh, now, in the PDFs folder, there's like a PDF called Biochem Redox, and it's basically just like redox applied to like molecules because in general, like the Gen Chem kind of definition of like loss of electrons, oxidation, gain of electrons, reduction is less kind of useful for like, you know, on a molecular kind of basis. It's like more useful for like, changing oxidation states of metals and stuff. But if we know that a sugar, like a monosaccharide like this, has a hemiacetal or a hemiketal, and then what I'm talking about from the Biochem redox PDF is that you can oxidize an alcohol, like if it's a secondary alcohol or a primary alcohol, you can reduce them to the secondary to a ketone, you can reduce the primary to an aldehyde. Um, so basically, this with an OH here, like here, it's not, it's like a primary or a secondary alcohol, but it can be oxidized, right?
Yeah.
But now, if we think about what happens when we make a glycosidic bond between like two sugars, we could have like an OH here. So like between the, so it's one, two, three, four, five. I mean, I didn't draw the entire thing, but we can make that. One, two, three, four. So you could have a bond made between the one hydroxyl and the four hydroxyl of a different glucose. And it'll be just like the other ones, like dehydration synthesis or condensation. And this will give you something that looks like this. And we can see now that if we look at this again, this now, so this OR was this over here, right? So the OR is still there. But now this is another OR, right?
Yeah.
So we don't have any more hydroxyl groups here. And now this, instead of being a hemiacetal, this is an acetal. Okay. And then if we started off with a hemiketal and we got rid of or replaced the hydroxyl with another OR, then that would just be a ketal, right?
Yeah, I guess I'm just kind of confused about what an acetal is. Is it because there's two R groups, that's why it's a acetal now?
Oh, when you say R groups, do you mean OR groups?
Yeah, O R, yeah.
Yep.
Okay, that makes sense. Okay.
Yep.
But I guess I'm confused because I'm like, well then what's the difference between the acetal and the ketal?
Oh yeah, so that because I only drew one. So basically, if there were just two R's down here,
Oh, okay.
yeah, it's like the acetal is kind of like a way of saying aldehyde.
Yeah, that's what I was thinking. Okay.
Yep.
I just wanted to make sure I was on the right
Hmm.
path.
Yeah.
Okay.
So now the thing. Okay. So now for a disaccharide, there could still be at all the way at the end of it a free like OH group, just like we had over here.
Hmm.
So this one could still be a hemi, like either hemiacetal or hemiketal. Now, to tie all this together, what we're testing for with the silver mirror and stuff like that are we're testing for reducing sugars. Now, if a sugar is reducing, like ing, it means that it reduces other things, right?
Yes.
And if it reduces other things, it itself gets oxidized, right?
Mhm.
So then we can ask ourselves, is that it like if we are trying to find if something is a reducing sugar or not, is this a sugar that's capable of being oxidized? In in other words, that means that if it's a hemi, it indeed can be oxidized and therefore can be a reducing sugar. But if it is a non-hemi, like a full acetal or a full ketal, it cannot be oxidized, and therefore it is not a reducing sugar. And now bringing this all the way back to the silver thing. So there's like two tests for reducing sugars. There's like the Tollens test and Benedict's test. And what they basically test for, um, well, they test for reducing sugars, but the difference between the two would be so the Tollens test uses like a silver ion, which, I mean, there's more stuff to it, but in general, there's a silver ion. And if a silver ion gets um, reduced, which means it, gains electrons, it can turn into silver solid, right? Um, and if something's a solid, it's neutral.
Mhm.
So this had to have, if it's starts off as a positively charged silver ion, in order for it to turn into neutral silver, it needs to gain electrons, right?
Yeah.
So now the silver solid looks like a mirror. So that's what they mean here. And then Benedict's test is a similar test, except you start off with copper cation, and then if this gets reduced, it turns into copper solid, and this is described as a brick red precipitate. So, um, so yeah, so this is essentially asking us, if you take like one of these disaccharides and you put it in a solution of this silver here, and like which will not result in the silver mirror. So the silver mirror happens if you have a reducing sugar, but if you do not have a reducing sugar, you won't have the silver mirror.
I see. And the reducing sugars are sugars with extra hydrogens, or I guess like I guess yeah, or
So if you have any type of hemiacetal or a hemiketal, that can be a reducing sugar. But if you have an acetal or a ketal, it can't be a reducing sugar.
okay. Let me look at them really quick.
Hmm.
Um, Oh, this one looks like I think it's a hemiacetal.
What's it?
Yeah, is it not a hemi? Because like okay, so like I guess like looking at this X here, wouldn't it be this carbon?
So now, well, you're looking at the right, so yeah, from that, see if you have like an OH or an OR.
Oh, this is actually it's a acetal, not a hemi.
Mm-hmm. Because we have OR, OR,
And then there's the H there.
mhm,
Okay.
H, and then an R.
This one is also
Mm-hmm.
uh an acetal. This one it's going, this one's just a little shaped weird. I think this one is also a acetal as well.
Mhm.
And this one is so I get yeah, it's an acet. Aren't they all acetals?
Yep. So basically, any glycosidic bond. So just like we talked about knowing like the functional groups for like the biomolecules, same thing for this. For like any regular sugar, like monosaccharide or something like that, it'll have hemiacetal or hemiketal. But when it forms a glycosidic bond like this, it'll no longer be that hemiacetal or hemiketal. It'll become the acetal or ketal. So the glycosidic bonds will always be like non-reducing. But remember how I said you could still have the last like sugar um form a hemiacetal or a hemiketal, right?
Yeah.
So if you look here, this is OR, but OH here. So this could be a hemiacetal, right?
Yes.
So so basically, like your glycosidic bonds will always be like acetals or ketals, no hemis, so they can't be reducing. But the one
Hmm.
at the very end of a, disaccharide or polysaccharide could still have a hemiacetal or a hemiketal there. So it could still be a reducing sugar.
Okay. I see. So okay, they all have except for this one.
Yeah,
So
good.
that makes okay.
Yeah. So this was good because this like covered a lot of good like topics. So I would say like as you continue to practice, when you look at these sugars, to be able to identify your functional groups like we do for any other type of biomolecule. So you want to look for like, okay, where's the hemiacetal, where's the hemiketal? And do we have, an acetal here or a ketal here instead of the hemi? And then from there you can see if something is going to be a reducing sugar or not. Because if it's a hemi, it can be a reducing sugar. And
Hmm.
result in a silver mirror or brick red precipitate. But if it's not, then and there's no Hemi, it's just acetyl then it won't produce that
Okay. Can I take a picture of this real quick
first.
for my notes?
Hmm.
Thank you. Mm. I thought this was a Lewis acid Lewis base reaction, but I was wrong.
Uh,
Maybe it's oxidation reduction.
yeah, so here we can see that this magnesium solid has an oxidation state of what? Or like charge of what?
See, it doesn't have a charge. It's 0.
And then what about?
Oh, and then it goes to 2 plus.
Hmm.
Okay.
Good. So magnesium's oxidation state changes, right?
Mm-hmm. Damn, I feel like I should have caught that. I thought
Hmm.
that it was a Lewis acid because from my point of view, it seemed like the
Hmm.
HCl was giving its. I mean, but I guess that's not really because I know a Lewis acid Lewis base is about giving electrons
Okay.
or doing remaining electrons. So I thought like
So
the chlorine.
this is an acid, right? Which would dissociate into H plus and Cl minus, but doesn't seem like it's protonating anything, right? It's like
Yeah.
this H is plus one, right? And then here
Hmm.
H2 is zero, right? So we have the oxidation states changing.
Hmm.
So that'll make it a redox reaction.
Gotcha. Okay.
Mhm.
Um, and this one's talking about ultrasound.
Mm,
Um,
yeah. So this is kind of asking us about um Doppler and asking us like what minimum information we need for the Doppler effect. So we have, for instance, like the speed of, so the S will mean the source of the sound, the speed of sound itself, um, frequency of the source, and I guess frequency that is observed, um, velocity of the observer, and what minimal information do we need to, like, meaning, like, this is all the information that can go in, but we don't need it all uh to do to
I
like.
feel like
Mhm.
I think we just need the frequency of the sound, frequency of the observers,
Mhm.
and then velocity of the source.
Okay, let's see. So the velocity of the source, let's see, we could um
Okay, I guess we don't need that.
because I think that the, like, okay, if the observed frequency is larger than the actual frequency of the source, that means that the observer and source are getting closer together, right?
Yeah.
And then if if it's, if the observed frequency is smaller than the source, they're getting further apart. So I think the frequency of the source and the observer uh, can give us information about the velocity of the source and the observer, but we would still need the velocity of sound, right? Because then we
Hmm.
can see, um, based on that, like if the source is moving towards it or towards the observer or away from the observer. Um, so yeah, I think it'll just be the frequencies of the sound waves uh, emitted and observed. Emitted is just same thing as the source frequency. Observed is a observed frequency. Speed of sound is speed of sound. So yeah. So I guess the main thing here is that you don't need the speed of the moving object. I think that could be a way uh to look at these choices and see how they're different or I guess um yeah, I guess to see how they're different and then asking yourself like do we really need the speed of that moving object?
Gotcha. Okay. Doing a little too much. Let me see something. Okay. Yeah, I feel like this passage had me a little confused.
Okay.
Um,
So um So yeah, we might not have time to do the entire passage, but for this question at least, if we look at this table here, it says that like okay, the BSA CPFX binding experiments in the presence of warfarin and ibuprofen, and it says note K naught or K0 represents the affinity constant of CPFX in the presence of BSA only. So we want to be very comfortable with ratios, right? Because so if Ka over Ko is less than 1, what does that tell us?
that KO is bigger.
Then Ka, right?
Yeah.
And since we see these values are less than 1, and they're telling us Ko is the affinity when you just have BSA and no warfarin or ibuprofen, we know that, well, the BSA CPFX binds better when you don't have warfarin or ibuprofen, right?
Yeah.
And now for table 2, same kind of thing, BSA CPFX binding experiments. This time, instead of in warfarin and ibuprofen, it's in the presence of metal ions. And then K naught is the binding constant when you don't have the metal ion, right?
Yes.
And since we see that these values are less than 1, it must mean that K0, yep, which is the binding when you don't have the metal ion, is larger, right? Than Ka when you do have the metal ion,
Okay. Yes.
right? So this means that so basically what we're looking at is here, and we see that these are all less than 1, which means K0 is greater than Ka. And since they're saying K0 is when you don't have the metal ion, and it's a larger value, that means this binding is stronger when you don't have the metal ion. So metal ions present in plasma are expected to,
They would decrease. Wait, hold on. Yeah, decrease the amount of,
Mhm.
yeah.
Now, let me ask you this
That
though. Yeah, so that's right. Now, if you decrease the amount of CPFX bound to BSA, what does that tell you about the amount of free CPFX?
it's increasing.
Mhm. Because CPFX could either be bound or free, right? So
Yeah.
if less of it is bound, more of it will be free. So that's why this one, if this said increase in the amount of free CPFX, that'll work, right? But yeah,
Yes.
looking at these ratios and being really comfortable with um, when a ratio is equal to one, when it's greater than one, when it's less than one.
Okay. So we don't, are you, how much time do you have left? Like a few minutes?
Um, yeah, I could do a few more.
I mean, it's chill. I was just gonna ask, so like moving forward,
Hmm.
would you suggest that I just do just like more Chem Phys practice questions and just kind of like focus on getting as many reps in to increase my score?
As many what in?
I guess like questions.
Uh-huh. Yeah, yeah. And so I would say like as you're reviewing this to really understand like what well yeah, like I guess like what they're asking for and then trying out, like I don't know if you've done your like blind review or
One
anything
second,
yet,
one second.
but um oh yeah, were you able to do like a blind review or anything like that yet?
No, not yet.
Okay. So yeah,
Um,
try that. So like, write down which questions you got wrong and then try doing exactly what you're doing here and then just trying those
mhm.
questions out. Um, and then, do your regular review where you read the solutions and stuff. But yeah, I would say to really make sure you understand like the questions that you got wrong on this CP section. And to I guess look more into like functional groups, identifying them, and then like being able to like kind of read these tables and kind of like taking, okay, what can I use from the table? And what can the table tell me with like the ratios and things like that. So I would say, yeah, to do your blind review and then your regular review, and then we can meet sometime to kind of like solidify these CP topics. Um, and that overall you're doing well. So let's just nail down these CP stuff.
Okay, cool, cool. All right, well, thank you so much.
Yep.
How much is it for today?
So 113.
Gotcha.
Yep.
And
And
all right,
good luck. And I will
thank
see you
you.
sometime soon. All right. Take care.